Swayam Prabha. Digital India. Educated India.
Okay. All right. So let me tell you one cryptographic tool that's useful in building zero-knowledge proofs, and that's called commitment. Look, it will sound a lot like encryption, but its properties are different. So commitment is a two-stage protocol, you could say, between a sender and a receiver. In the first stage, the sender commits to a value. What does what does that mean? It's like the sender puts this value, write it on a sheet of paper, put it inside a box, lock the box, and give the box to the receiver, but not the key, right? So at this point, the receiver is holding the box. They know there is a sheet of paper in there with some value, but they don't know what the value is. So at this point, it's hidden. Later, the sender can send their key over, and at that point, the receiver can open the box, read the value, and they know that this was the value that was sent in the beginning. There's no magic by which this paper got changed. So the value that I'm seeing now was what was committed to in the beginning. Okay. So that's commitment. It might sound a lot like encryption. You might think, why not encrypt and then send the decryption key? Well, encryption doesn't really guarantee that, maybe you can find two different keys which will decrypt the message into two different things. Clearly, if you're using one-time pad, you can do that, right? So encryption doesn't, by itself have that property. You can have encryptions which are also committing, but commitment is in some sense a simpler object. I'll not talk about how to build commitments from the simplest cryptographic assumptions, but I'll just mention this one thing. This is often done in practice. You can build a commitment protocol in the random oracle model very easily. To commit to a value x, you pick a random string, long enough random string, concatenate it with x, and then hash them together. Hash, that's you may call the random oracle, and that output you send as your locked box. And then to open the box, you send x and r. And the receiver should check that x and r do hash to the original committed value, and if they did, then since it's a random oracle, to begin with, if the output is long enough, there is negligible probability that there exist collisions. But even if there are collisions, it's hard for the sender to find them. Of course, assuming the output is long enough. So it's a binding commitment scheme. It's hiding because this R is long enough, right? Otherwise, you could just try. You're guessing, if this X that you committed to, if that R is short, I could run through all R's and check what you committed to is X or not. So the hiding property comes from R being long. The binding property comes from the output being long. Of course, all of this when the oracle is a random function. I should repeat the mandatory disclaimer or caution that the random oracle model is only a heuristic model. You can do things in that model that cannot be done at all. But commitment is not one of those things. Commitment we know how to do in the standard model too. It's just that this is simpler to describe, or even people in practice use this. Okay, so now why did I tell you about commitment? I was talking about zero-knowledge proofs. Well, here is an example of using commitment. So the previous examples that we saw, graph isomorphism, graph non-isomorphism, there was no cryptographic component to it, other than this, picking things at random, challenging. The protocol was just apply permutation, send them. There was no, encryption, commitment, nothing. I'm now going to use commitment to get a zero-knowledge proof for this problem. So the kind of claims that Alice is now trying to prove is that there's a graph that Alice and Bob know, And Alice knows how to color this graph using 3 colors. What does it mean to color the graph? You have to assign, every node. You have to assign a color to every node, one of these 3 colors, and such that in every edge, the 2 endpoints have different colors. Okay, so there is no monochromatic edge. There's no edge in which both colors are the same. Both endpoints are the same color. Okay, that's the graph coloring problem. The graph coloring problem is to find a coloring or to even find if a coloring exists or not. Okay, so in this case, it's a 3 coloring that we'll be talking about, or you could think of. Okay, so here is the knowledge proof for graph 3 colorability. So the prover is this guy now, has a 3 coloring. So he has a graph, and it came colored to him, so he knows that it's 3 colorable. He wants to convince the verifier that it's 3 colorable without revealing anything about the coloring, other than, of course, what she might herself be able to deduce, right? By looking at the graph, she might know something about the coloring. You don't want to reveal anything more. Okay, so we're going to use a commitment protocol as follows. So first, the prover will, now for clarity, I'm using a different color palette here. He will assign, so the red, blue, and green colors is what he's going to use in the proof, and he will assign them randomly to the original colors, whatever they were, the kind of pastel, red, blue, and green, or red, I don't know, orange, blue, well, orange, cyan, and yellow, maybe. So you will assign it randomly. You will say, okay, cyan is going to be blue, yellow is going to be red, orange is going to be green, right? He'll make a random assignment of colors, the new colors to the old colors. Okay, so now there's another graph 3 coloring, yeah?
Certainly if a graph is 3 colorable, then there exist many different colorings, like possibly.
Yes, so the question is, if a graph is 3 colorable, there could be many different ways to do coloring. The prover got some witness and he's just going to use that. Okay? And what we care about is that we don't reveal anything about this graph beyond what the verifier already knew. Anything about this coloring or other colorings, or she shouldn't learn any information from this protocol. Shouldn't gain any knowledge from this protocol, other than the fact that this graph is 3 colorable. Okay, that's a goal. Okay, so in the proof, I want to start with, this is an efficient prover, so I want to give him a coloring to start with. So he needs some coloring, and then he can run the protocol. It doesn't matter which one we give. Okay. Okay, so he sends this, recolored graph, but not. Of course, if he sends it to the verifier, she learns a lot, right? You don't want to do that. So he just commits to the colors. So that's why it's black. So they are all hidden under a flap, right? And inside a box. So she just knows, okay, you are claiming here are some colors. I can't check if it's a good coloring or not right now because they're all hidden colors. She wants to check though if it is actually a good coloring. So she will say, okay, I picked a random edge. I picked an edge at random, and show me the colors of this edge. Okay, show me that this edge was not monochromatic in your coloring. Okay, so the prover would verify those two. Okay, so and what does she check? She checks that it's not monochromatic, that there are 2 distinct colors. Okay, so she knows the colors are going to be red, green, or blue. And what she got is red and green. Okay? So that's fine. If it was red and red, she would say, I'm aborting or I'm rejecting your claim. If it's different colors, she is okay with that. Okay? So if they're distinct colors, then she would say okay. And let's see, why is the sound? Okay? As you can imagine, we'll repeat the whole protocol many times. But as it is, why does it have any soundness guarantee? So if there was no valid coloring using red, green, and blue, there is at least some edge where it's monochromatic, or they are not valid colors at all or something. There's some edge that the prover couldn't have opened into two distinct colors. If he could have opened every edge into two distinct colors, then there is a valid coloring, right? Then it is three colorable. So if it is not three colorable, there is at least one edge on which he would have got stuck. So, and that edge will be picked with probability at least 1 over the total number of edges. You're picking an edge at random. There could be multiple edges in which he could get stuck, then this probability is higher. But at least with probability 1 over the number of edges, you would pick an edge which is not properly colored. Okay. So if the statement was wrong, then there is at least probability 1 over the number of edges for the verifier to catch the prover. And we will repeat this many times, but it's important that we will repeat it many times with independent reassignments of the color. We're always using red, blue, green, but first I said cyan was mapped to blue or whatever. Next time cyan is mapped to red, blue, or green independently, right? It's in the next trial. So we will do this whole protocol many times, starting from assigning the random colors, right? And if after say 100 trials, every time Bob passed, then that's convincing. You need to do a little calculation to see how many times you need to repeat. So if the graph is bigger, you need to repeat proportional to that. So it's the number of edges times some security parameter, number of times that you would repeat. Okay. So is the protocol clear?
The colors are fixed, like the three colors which are used.
Yes. So always it's 0, 1, 2 or red, blue, green. The three colors that are supposed to be committed, they are always the same. Okay. Yeah. Otherwise, you could just use more colors to color, and nobody will know. Any other question?
Aren't you revealing some information when you type the color?
Okay, good question. So seems like we revealed a little bit of information, right? We revealed two edges, two nodes. So maybe I don't have a description here. I'll just tell you why. So what is the verifier's view? Verifier sees a random, all the black things, so they are commitments, and then she sees, she picks an edge, and she sees two random colors. No matter what the original coloring was going to be, this is what she was going to see, two random colors. This is something she could have simulated by herself. How would she simulate it? I kind of showed it as if it's a physical thing. The commitment is some cryptographic string, right? It's a encryption. So what does the simulator do? Simulator would first decide what the edge is, decide what the colors are, all of them at random, two distinct colors. And then it'll put junk into all the other nodes. And then she'll commit to all of them. That's what the simulator would do. And then simulator would say, okay, so that was my commitment. Then this was the edge that was queried. And hey, here is how it was revealed into these two distinct colors. Right? And it's important, and when it's repeated, for the simulation to work, it's important that they are random. Otherwise, of course, if you next time you ask this edge and you had not recolored it, then you're learning something. But if they are independent recolorings, then the simulator just creates a bunch of independent simulations of this form with independent commitments, and it's a good simulation. It's a good simulation assuming the commitment is hiding. In real protocol, the commitment is to a proper coloring. In the simulated view, the commitment is to junk, right? The other things are all maybe the same color. And you cannot tell the difference because commitment is hiding.
Every time she's asking for a new edge, they shuffle the colors, the assignments.
Yeah, so it's on a new commitment. So this entire protocol is repeated many times, starting with pick random colors, create a fresh commitment, then she asks for an edge, then he reveals. So that whole thing is repeated all over the
So for the new simulation, colors would not be green and red.
It'll be again a fresh independent pair, a random pair of colors. Okay. Yeah.
So if the verifier picks the edge as per his or her wish, then if like the red node, if more than 3 times he picks the one of the edges corresponding to that node, there is the possibility that it will have red color only on that node, and then they will get to know that for this setting, what is the color of the vertex of the
No,
node.
so that's exactly, so your question is, by doing it multiple times, by choosing edges carefully, like, say, you choose this edge next time, wouldn't the verifier be learning something? She's not learning anything at all, because next time she picks this edge, what she's going to see is 2 fresh random colors. Even if one of them is red, the other one, even if she chooses the same edge again, and even if she saw red here, the other one is going to be blue with half probability, green with half probability. So in the next coloring, the colors don't have any meaning compared to the previous color.
There is a 1/3 probability that the one of the colors is red, like the vertex which is colored red this time, that will be red again the next time.
Yes,
in
yes.
random color.
So it is important that it could be red. So let me, I'm not sure if I'll be answering your question, but let me point out another thing so that you can think about this probability aspects clearly. So let's think of one-time pad for a second, right? Say I'm encrypting a bit string. With some probability, my key could be the all-zero string, in which case I'm sending the message in the clear as it is. Okay? Does that mean I should not, when I see the all-zero string, if I keep it aside, then it will actually become insecure? By seeing the ciphertext, you will learn that it is not. I'm relying on the fact that with some probability, it will be the all-zero string also. And similarly here, when I'm recoloring, it's independent. With some probability, yes, the coloring will be the same, or coloring will be the same for one of the nodes, one of the colors. I do want it to be the case. Okay, otherwise the views are not simulatable.
So like we said that on repeating the experiment multiple times, that probability vanishes.
No. Okay. On repeating many times, what probability vanishes is in the soundness side of things. What I said is the probability that, so the malicious prover is sending some arbitrary junk. We know that maybe almost good coloring. We know that in at least one edge, the coloring cannot be good. And with some probability, we'll get that. We'll get it only with a small probability, 1 over the number of edges. Okay, so that is a small probability of catching, and we need to amplify it by repeating it many times. So that's about the soundness part. The question about whether the verifier learns something, that's the zero knowledge part. And for that, the argument was that the whole view can be simulated by first picking. So how is the simulator doing again? So it picks an edge. For the 2 nodes on the edge, it's picking random colors, fresh each time. Okay, and then making a whole commitment where exactly those places are. It's like drawing the bullseye around your arrow. You're saying, okay, you would have asked me to open this edge. My arrow is already that edge, the 2 nodes on that edge, and then the challenge here, the edge, is the target that's going to come. I'm doing it after I have picked. I've already set it up so that I can answer your challenge. Right? The challenge is written so that it becomes around my arrow. So I picked the edge myself, as in I hit somewhere, and then I'm saying, oh, your challenge was actually that same place. Right? So you should think through this. You should think through this and convince yourself that this is a valid zero knowledge protocol. Okay? But why do I want to mention this particular example is the significance of this particular problem as opposed to graph isomorphism or graph non-isomorphism is that graph 3 coloring is an NP-complete problem, which means for any problem in NP, you can take an instance in any problem, any other NP problem, and there's a way to transform that into a graph 3 colorability question. We can transform that instance into a graph such that the graph is 3 colorable. So here is what it is. So suppose there is some language L which is an NP, you can transform that, for any x, there is an efficient transformation into some graph related to x, some graph representation, if you will, of x, such that x is in that language if and only if this graph is 3-colorable. Okay. So now, to prove to you that x is in the language, all we do is that the prover and the verifier will transform x into g of x, and the prover will give a proof that g of x is 3-colorable. Right? So by having a protocol for any NP-complete problem, you essentially have a protocol for every problem in NP. Okay? So that's why it's significant. There are many other protocols. There's just one of the earlier ones. It's kind of cool and nice to explain. But there are many other protocols for NP problems in general. All right, so the last thing I want to mention, actually we'll go back to something we saw yesterday. We talked about signatures, flashed the particular signature scheme, Schnorr signature, and said it probably looks mysterious. I want to demystify that. But I also want to tell you about another notion of proof, and that's a proof of knowledge. Okay? So proof of knowledge is, say it's something like, I know the inverse of this. There's a permutation. I know an x such that f of x equals y. So you know y, and I'm claiming that I know an x such that f of x equal to y, without showing you this x. Okay? Now, the fact that there x is an x is guaranteed, just from the mathematical property of this f, let's say. So everybody knows f is a bijection. So it's not really, my proof is not actually about claiming that there x is an x. I actually want to tell you, I know this x. So there's another kind of philosophical question. What does it mean for me or a machine to know something? Okay? We already kind of handled that with zero knowledge to say it knows nothing. We said, oh, that means it could have been simulated. Whatever it saw, it learns nothing, we said, no. It could be defined as saying whatever it sees could be simulated by itself. Similarly, here we are going to have a notion of what does it mean for a machine or an algorithm to know something. We'll say, okay, I will say it knows something if there is a way to look at this machine or algorithm, and if I look at its registers when it's running, I may not actually see this thing that it's supposed to know. Right? May not see it in the clear. But there is some efficient algorithm that can extract that and write it down on the side. That's what a knowledge of, and that what an algorithm knows something would mean, is that you can look at that algorithm and there's some way to extract this information from that algorithm. Maybe by running this algorithm many times. Okay? So in terms of, so this is a soundness notion. It's a guarantee to the verifier. Earlier, soundness just said, if you accept the proof, that means x is in the language. Now we are saying, if you accept the proof, then the adversary actually knows the witness. So if an adversary has a non-negligible chance of convincing you, or a significant chance of convincing you that, convincing you as in making you accept the proof, then there is a way somebody would have gone into the head of that adversary and extracted a witness in the clear. Okay, that's a claim. Okay, so let's see zero knowledge proof of knowledge for discrete log. So there is some group, story from yesterday. There is some, say it's a cyclic group. There's a generator, and there is a group element capital Y. And the prover is claiming, I know the discrete log of capital Y to the base G, namely this little y. Okay, and I want to prove to you without giving you this y. Okay, so there's a statement in NP. One way to prove this would be to use an NP reduction, right, to change this instance of capital Y and the group's description and everything into a graph for graph 3 colorability. That's a very inefficient, or it blows up things a lot. Okay, so you don't want to do that. So here's a much more direct proof. This is the entire proof. It is what's called honest verifier zero knowledge protocol. So let me just go over the proof. The prover picks a random group element, in a way that it knows the discrete log. So it picks a random little r and computes capital R. And it sends this capital R to the verifier. The verifier picks a random x in the, so there's a cyclic group or a prime order group, and say, the order is p. Then this x is an element in the range 0 to p minus 1 to p minus 1 to p minus 1. Okay. What the prover needs to respond, if it knows y, this is a simple computation, it needs to respond with xy plus r, because it knows this little y, it knows r, it got this challenge x, and it's supposed to respond with xy plus r. Now the verifier cannot check this right away because it doesn't know that's what it did, right? It doesn't know this little y. So it knows x, it doesn't know r either. But it knows everything in the exponent. It knows y in the exponent. It knows r in the exponent. The capital R is little r in the exponent. And it knows x in the clear. It knows x as it is. So it can compute this xy plus r in the exponent. Namely, it can compute g to the power s by, so if you look at what this is, y to the power little x is g to the power xy. Times r makes it plus little r in the exponent. Okay? So it can check this. And by checking this, it's convinced that s is indeed xy plus r. Okay? So it can check at least that part, that what the prover send you is xy plus r. And now the idea is that somehow the ability of the prover to send xy plus r when you asked a random x is it could have done it only if it knew y. Okay? It could have extracted y from a prover who is able to answer these challenges on random x's. So why is that? By the way, there's also a zero knowledge part to it. Maybe I'll first mention that. The zero knowledge part is just by picking this. Well, you can simulate it by first picking s and x, and then computing this capital R. Okay, so you pick s and x and compute capital R according to this equation. That's how you would simulate, and that's how you draw the target around your arrow. But let's talk about the proof of knowledge, which is what I want to mention here. So as I said already, by verifying this equation, you are verifying that s is indeed xy plus r, where that little r is defined as the discrete log of capital R. Now imagine, so first the prover sends you this capital R, and as a verifier I could have sent you any x, right? And imagine so if you only could answer one of these x's, your chance of convincing me is negligible. The group is very large, this x is coming from a large space. So to have some reasonable probability of convincing me, there should be a good fraction of x's on which you will be able to answer. Suppose you could have answered on at least two different values of x. Okay, so some x1 and x2 on which you could have given me this answer, an answer that will convince me. So this w1, w2 is s1, s2 basically, you could say that. If you have two such answers, then I can solve for y. It's a linear equation, okay? And we are working modulo prime, so you can do, it's a finite field, if that makes sense to you. You can do division basically, right? You can get, when x1 and x2 are distinct, these are two linearly independent equations. You can solve them just the way you would solve it. Division by x1 minus x2 will make sense because we are working modulo prime. And yeah, so this was the fact that it's a proof. This was the extractor. If you have a prover who could have convinced you with a little probability, then there is a way I can take that prover and basically extract this from it. There's a little more to say how exactly the extractor will work. It will actually run the prover, get this capital R, make two copies of the prover at that point, the prover state, and send different challenges to it. And if it manages to get answer for at least two of those instances, an answer that is verified, then it can solve it. Why would it get 2 answers? Well, if the prover had some reasonable chance of convincing you, then you will hit that by making random X queries. You will see it. If you have a good chance of seeing it once, you have a reasonable chance of seeing it twice also. Right? The probability is a little smaller. So if you try long enough, you will see it with very high probability. So that's, does that make sense? Just the proof of knowledge part. Okay. So, and I already said it's zero knowledge. And now I just want to point out why Schnorr signature was very similar, or was essentially doing the same. There's a slight variant of the Schnorr signature I had in the slide yesterday, but it's essentially the same thing. There is some plus minus difference, and then this signature yesterday was to send not the capital R, but this G to the S. But capital R versus G to the S is not very different. You could say signature sends all of them. One of them can be computed from the other. So let me rewrite the Schnorr signature as follows. You pick an R first as G to the power little r. Now in the protocol, so there's one big difference between signature and a proof. In a proof, you are talking to a verifier. It's an interactive protocol. In signatures, you are sitting down and writing down the entire signature, which is like a proof, and sending it to a verifier who is not there to interact with you. It's a non-interactive process. So we'll use a random oracle here. So this X comes not from a live verifier, but from a random oracle. So it's like you send this R to the random oracle, and the random oracle will respond with this challenge X. Okay? So this whole protocol here could have been made non-interactive in the random oracle model by setting this X to be a hash of G to the R. Okay? Hash being the random oracle. And it would have been still a sound proof system, sound and the proof of knowledge. So here we are going to do the same. X is going to be a hash applied to this R, okay? R, and maybe you could include Y also if you want. In this non-interactive proof, you might want to do that. But more importantly, here you will also include the message M. That's another difference between a signature and a proof. The signature is on a message, and you want to say something like, even after seeing many signatures on many messages, you cannot create a signature on another message. So this signature, this X is kind of tied together with this M, okay? And the rest of it is the same. The proof is just this S equal to XY plus R, and the verification is exactly this, where X is now computed as the hash applied to M and R. So okay, signature has R. You already know M, so you can compare this. So hopefully that makes sense. Where this is basically underlying what's called DSA, the digital signature algorithm. So hopefully that makes sense. If you just look it up on Wikipedia, you probably wouldn't realize where it's coming from. It's coming from a zero knowledge protocol. Okay, so that's all I had for this session. We'll continue in the next lecture with secure multi-party computation and a little bit of digital cache. All right, so I'll see you. Any quick questions before we break?
So in the previous slide, what was that W1?
Sorry, I should have, it should be called S1, S2.
But sir, the prover knows small y, right?
The prover knows little y.
So what is it?
The proof of knowledge is not a guarantee to the prover. We are telling that the prover might have done some complicated program. They may not have followed our protocol. So they may not have used our y. They may not actually have had a y in the clear. They did some complicated thing. We want to say no matter what complicated thing it did, I can take that prover and run it as a black box actually, run it a few times though, and extract this y from it.
So like S1 and S2 were computed from y, right?
Need not be. All I know about S1 and S2 are that they satisfied this equation, the verification. They may not have been computed from y. Okay, so just from the fact that the verification succeeded I'm guaranteeing you that there's a way to extract little phi from it. And clearly that shouldn't happen from interacting with the prover just once, because that's supposed to be zero knowledge. But by interacting it with in this 2 threads, right, after getting this R, you are kind of splitting into 2 parallel universes. And if you got to interact with the prover in both those universes, then you will be able to extract Y. In real life, you can interact with only once. Right. Any other questions? All right, so we'll break and continue shortly.